Okay, parametric differentiation. So if you recall, a parametric definition of a curve is rather than having y as a function of x, we have x and y both as functions of a parameter t. So we call t a parameter. And this is a parametric definition of a curve. It just gives us a little bit more freedom as to what curves can look like on the xy plane without compromising what it means to be a function. So what we're going to look at today is parametric differentiation, and we are essentially going to apply the chain rule to this setup to find dy by dx. So by the chain rule, if you remember, dy by dx, we can say is equal to dy by dt times dt by dx. Okay. And you can see then that the dt's cancel, if you like. I mean, they don't actually, because these aren't fractions, but they behave like fractions, and the dt's will cancel from that point of view, and you're left with dy by dx. Okay, so we need to find dy by dt, and we need to times it by dt by dx, which is the same as doing dy by dt and then dividing it by dx by dt. Because when you times by a fraction, it's the same as dividing by its reciprocal, and it's easier to work with dx by dt rather than dt by dx. So this is what we're going to be working with, dy by dt divided by dx by dt, and we've got x as a function of t and y as a function of t. So this will tell us then that dy by dx is going to equal g primed of t, okay, differential with respect to y, divided by f primed of t, which is the differential with respect to x. And you'll notice that in this case, it's going to be a function of t. So when you're using parametric differentiation, you need to know the value of the parameter that you are looking at, not necessarily the value of x and y. If you have got x and y, you need to solve this system over here to find the value of t, to then plug it into here. Okay. Here, of course, use t as the parameter, but it might be something else. Another common letter that's used is theta, particularly when you've got trigonometric functions around. Okay, just bear that in mind. But the principles are the same. You differentiate y with respect to the parameter, and you divide that by the differential of x with respect to the parameter. And that's the premise of parametric differentiation. Okay, so let's have a look at some examples. So here's my first example. We're going to find the coordinates of the turning points on the curve, which are defined parametrically by x equals 3t into 1 minus t, and y equals 2t squared minus t cubed. And t is going to be between 0 and 2. This is one that I've used in the previous video, so just to remind you what that curve looks like, there we go. In the previous video, I think I went from t as minus 1, so actually it came down from up here and then spun around and did a little loop. But in this case, we're just going to go from t is 0 to t is 2. So that finishes over there somewhere. But the turning points that we have in question are here at the origin. So it does have a 0 gradient at that point, which we'll see in the algebra in a second. And up there, there's a turning point there. So the turning point is defined in exactly the same way as it would be with normal differentiation. You're setting the value of dy by dx to equal 0. Okay, so let's have a look at this. dy by dx, that is going to equal dy by dt divided by dx by dt. And what I'll do in this video is I'll shorthand a differential with respect to t as x dot and y dot. Okay, so if you see a dot above it, that means a differential with respect to t. If you see a y prime, that means a differential with respect to x. Okay, that's just the notation I'm going to use for this video. Okay, so y dot, differentiate that with respect to t, it's going to be 4t minus 3t squared. And the differential of x with respect to t, you've got to multiply out the brackets. So 3t times 1 is 3t, so differentiate that, you get 3. And 3t times minus t is minus 3t squared, so that's going to be minus 6t when you differentiate it. Okay, so there's my derivative, that's y primed, or dy by dx. And we want that to be 0 for a turning point. Okay, that's what it means to be a turning point. It means the y primed is 0, of course, providing that you're not at a stationary point of inflection, but we saw from the graph that that's not the case. So for this to be 0, we just need the top to be 0. So this tells us that 4t minus 3t squared equals 0, providing the bottom isn't 0 as well. And we can see the bottom is going to be 0 when t is a half. Okay, so when t is a half, we're going to get an infinite gradient. Yeah, you just need to make sure the bottom isn't 0 as well. Okay, I don't think at A-level you would necessarily have to consider that, but it's just something to bear in mind. So this is a quadratic with no constant, so therefore t equals 0 is a solution. And then I can divide by t, and I'm left with 4 minus 3t equals 0. So t also equals 4/3. Okay, so those are my two values of t. But that's not answered the question, because it's not asked for the values of t, it's asked for the coordinates. So we need the values of x and y. And to do that, we plug in our t values into our definitions of x and y. So therefore the coordinate when t is 0 is going to be 0 times 1, which is 0. And 2 times 0 squared minus 0 cubed is 0. So the origin is one of these points. And if you plug in t is 4/3, that's 2 times 4/3 squared. So let me get the calculator. Gonna need this one later anyway. Okay, so do 4/3, and we want 2 times that number squared minus that number cubed. And we get 32/27. Oh, that was the y coordinate. And the x coordinate is 3 times the answer into 1 minus the answer. And we get minus 4/3. And those are my two answers. Now if you look back at the graph, you can see that this is about minus 4/3 there. So we're in the right ballpark for our answer. And it's just a number that's a little bit bigger than 1, which 32/27 is just a little bit bigger than 1. So I'm happy that those two are the correct answers. Arguably this isn't a turning point for this graph because it starts at that point, so it's not actually turning. Questions in an exam wouldn't necessarily trip you up like that. But if I extend the range values of t, there you go, I've changed it to t is -1 now, it is now definitely a turning point. It's a local minimum and that's a local maximum. Yeah, arguably, if t goes from 0 to 2, arguably it's not a turning point because it's not actually turning at that point. It's because there's no values to the left of that point. Yeah, just leave your thoughts in the comments on that one. But I'm going to leave it as an answer to the problem. Okay, question number 2. A curve C is defined parametrically by these equations. So again, this is one that we have looked at before. This is one that was studied on the further maths course. It's called a cardioid. And I think this is a cardioid on its side. It looks something like this. There we go. And that is my x-axis. And that's my y-axis. Okay, so you can sketch that one out using parametric sketching, which is what I've done in a previous video. Now for this question, we want to find the equation of the tangent to C at the point P, where theta is 4 pi on 3. So here our parameter is theta, not t. And that's quite common when you're dealing with trigonometric functions. Leave your answer in the form ay plus bx plus c equals 0. Okay, so we're asked for a particular form for our answer. Okay, so first things first, we need to find dx by d theta. So I'm going to say x is equal to sine squared theta minus sine of theta. So x dot, which I'm going to use the notation for that for the differential with respect to theta. You can either use the chain rule or you can use the product rule for the sine squared, but whichever you do it, you're going to get 2 sine theta cos theta. And then sine differentiates to cos, so it's going to be minus cos theta. And then y dot, I need y first. We've got sine theta cos theta minus cos theta. So this time I do need the product rule on that. So I'm going to do this times the differential of that, which is cos times cos, so that's cos squared. plus that times differential of this, and sine theta times minus sine theta is minus sine squared. And then the cos will differentiate to a minus sine, so that becomes positive sine theta there. Okay, so there's my x dot and y dot, and that will allow me then to state that dy by dx is going to be this thing, which is cos squared minus sine squared plus sine, all divided by 2 sine cos minus cos. Okay, so that is my definition for dy by dx. Now, we want the equation of the tangent to C at the point P, and we're told at P, theta is 4 pi on 3. So I need 3 things at this point to find the equation of the tangent. I need the value of x, the value of y, and I also need the value of dy by dx. So let's plug in theta is 4 pi on 3 into these 3, x, y, and y primed, to get the 3 values I need. Okay, so I'm going to put 4 pi on 3, and I'm going to store that, if I can find the store button. It's that one. I'm going to store that as a, so I can just keep pushing a as opposed to, excuse me, as opposed to keep typing 4 pi on 3. Okay, so let's plug it into x first. So we're going to have sine of a, let's go put that in brackets just to make sure the calculator does what I want it to do, squared minus sine of a. Okay, and we're in radian mode, so that's fine. And we get, oh, not a nice number actually. I'm going to have to plug this one in. Plug this one in separately, unless the calculator's done something funny here. I was expecting a nice rational number. There we go. Let's just see if that was, yeah, it's completely different. No, it actually just squared the a. Okay, so it's 3 plus 2 root 3 on 4. That's the value of x. So the value of x is 3 plus 2 root 3, all divided by 4. Okay, and now y. So y is sine theta cos theta minus cos theta. Okay, sine of a times the cosine of a minus the cosine of a. And that's 2 plus root 3 on 4. And then y primed, that's going to be plugging it into here. And I've shorthanded it. So c is cos and s is sine. So it's going to be cos of a squared minus sine of a squared minus, no, I'm putting the wrong one in, aren't I? Oh no, I'm not, plus sine of a. And that's all divided by 2 times sine of a times the cosine of a minus the cosine of a. Minus 1. So my equation is minus 1. Okay, so I've got my 3 values. So therefore the tangent, so it's going to share the same gradient, is going to be y minus 2 plus root 3 on 4 is going to equal minus 1 times x minus 3 plus 2 root 3 on 4. And make y the subject. In fact, yeah, make y the subject first. So we're going to do minus x, and then I've got, that becomes a plus, and I'm going to add that as well. So I get plus 5 plus 3 root 3 on 4. And then I'm just going to times it all by 4 and neaten it up and put it into the form that it wants. Okay, ay plus bx plus c equals 0. So I'm going to leave the answer with everything on the same side. So it's going to be 4y plus 4x minus 5 plus 3 root 3 equals 0. Okay, that's in the form that it wants. And check the graph of that. Okay, so here's the cardioid. I'm just going to stretch it out a little bit so it looks more like a cardioid. There we go. And that is the equation of the tangent at the point in question. Okay, so there's our point. That's when theta is 4 pi on 3. And this is our tangent at that point with the equation we've just established.